कोई नहीं, डन।
ठीक है, हो गया लाइव। अरे माइक दे दो। माइक टेस्ट करने के कहना है कि चल ही रहा है, हो गया लाइव तो। हेलो, हाय एवरीवन, आई थिंक वी आर लाइव नाउ। हेलो, can someone please confirm if I'm properly audible? Hello, hello, am I properly audible? Can someone just confirm? Okay Deepak, thank you. ठीक है, yeah, thank you. Okay, so let's just wait for 10 more seconds and then we'll begin. Okay, so let's begin. Hello everyone, my name is Karan Masru and welcome to this session on final revision on computer organization and architecture. And today we will be solving some of the PYQs of computer organization and architecture. Okay, first of all, let's just have a look at the syllabus. So what's the syllabus for it? You have machine instructions, so how different types of instructions you do, and different addressing mode, right? Register addressing mode, direct, immediate, etc. Then you have implied addressing mode, etc. Then you have ALU, right, where the all the arithmetic logical unit is done, addition, etc. Then you have data path and control unit. Then there are pipelining, okay, very important topic, pipelining and pipelining hazards. There are 3 types of hazards. Then there is memory hierarchy, cache memory, main memory and secondary storage. And finally you have the IO interface, where you talk about the interrupts, different types of interrupts, and the DMA, right? Just a second, give me one more second so that I'll, yeah. So today we are going to solve some of the previous year questions, and today we will be solving some of the previous year questions of COA. Tomorrow we will be solving some of the previous year questions of DSA, and then afterwards on Thursday we will be solving previous year questions on digital logic. Okay, that's the plan. And on Friday there will be no revision because of a particular subject, because Friday is the last day, and on last day I would suggest everyone to just revise all the topics, okay, which you have already done. Okay, shall we begin? Okay, just give me a heads up, just write anything in the chat box, let's start or something, so that I know you people are following, at least 1 or 2 people. Hurry up. Okay, everybody is following, we'll start. Okay, let's start with the first question. This was asked in GATE 2022. It says that let R1 and R2 be two 4-bit registers that stores number in 2's complement form. Okay, so numbers are stored in 2's complement form. Okay, here the numbers are stored in 2's complement form. For the operation R1 plus R2, which one of the following values of R1 and R2 gives an arithmetic overflow? Hello, hi. Okay, so this is the question. So basically you see, when you have 4-bit registers, then what is the range of 2's complement? It is minus 2 की power n minus 1 to 2 की power n minus 1 minus 1. This is your range. I hope you people know how this range comes. Okay, no need to mug up the things. So this is how much? Minus 2 की power 4 minus 1 is 3 up to 2 की power 3 minus 1, that is equal to minus 8 to plus 7. This is your range. Okay, so when you add two numbers, if the result is going out of this range, then it will give you overflow, right? So what we will do is we will add the two numbers and see whether the result is within this range or not. Okay, now for the first case we have number 1011 and the second is 1110. Okay, now please remember these numbers are in 2's complement form. So just looking at the binary number, you cannot tell the value, right? How can you tell the value? You put a negative sign if the in 2's complement, if the MSB is 1, then the number is negative, and if the MSB is 0, then the number is positive. If the number is positive, you can directly tell the value looking at the number. If the MSB is 1, number is negative, what you do is you put a minus sign and take 2's complement of the given number, and this will be the positive magnitude. Okay, so you take the magnitude after taking 2's complement and attach a negative sign. Okay, and if the MSB is 0, number is positive, you can directly look at the number and tell the value. Clear hai? So here the numbers are negative. So what I'll do, I'll take minus sign, I'll say minus and 2's complement of this. What is 2's complement of this? So there are two ways to find 2's complement. One is take 1's complement and add 1. Another is the shortcut. What is the shortcut to find the 2's complement? Starting from the right hand side, copy the bits as it is until first one is encountered, and then flip the bits. So when you encounter the first bit, up till there copy as it is, then flip the bit. So this will become like this, and R2 will become negative of this number is also negative. So you copy the first two bits, now you encounter the first one, now flip the bits. So this is how much? Negative 5, because this magnitude is 4 and this is 2. So this is negative 2, negative 5 and negative 2. When you add these two, you get negative 7. Negative 7 is within the range. So this will not give the overflow. Clear hai? Let's look at the second one. So R1 register has a negative number. So I'll put a minus sign and take 2's complement. What is 2's complement? 0, 0, 1, 0. Starting from the right hand side, copy the bits until you encounter the first one, then flip the remaining bits. And what is R2? This is also 2's complement. This is also negative. So you take 2's complements. So you take 0, 1, 1, 0. Now this is how much? Minus 4. This is how much? Minus 6. When you add them, you get minus 10. This is not within the range. So this will give you the overflow. Is this clear? Let's also do for the two remaining. If you wish, you can do. Both the numbers are positive, so you can directly look and tell the value. This is 3, this is 4. 3 plus 4 is 7. 7 is within the range, right? And last one, this number is what? Minus, first number, this R2 is minus 1. This is R2. What is R1? It is negative of 1, 1, 1, 0. This is 7. That is minus 7. Minus 1 and minus 7 is minus 8. That is also within the range. So this will also not give overflow. So option B is the correct answer. Is everyone following? Please reply. Is this question clear? Any doubts? This was asked in GATE 2022. Okay. Guys, if there is doubt, ask the doubt, otherwise please reply quickly whether it is clear or not, so that we can cover more things. Okay. Is this clear? Shall we move to next question? Okay, great. Let's move to next question. Okay. Try this question. This was also asked in GATE 2022. Okay. Okay, Pranav. Thank you. Please keep replying. Please keep the chat box on, so that I also know you people are following. Okay. What does this question say? A cache memory that has a hit rate of 0.8 has an access latency of 10 nanosecond. Okay, means out of 100 operations, 80 operations, out of 100 things which you want to access, 80 things are already present in the cache. Okay, that is the hit rate. And access latency is 10 nanosecond, means once you have a hit to get that data, it takes 10 nanoseconds. And miss penalty is 100 nanosecond. What does miss penalty mean? If there is a miss in the cache memory, you need to go to the main memory and bring the data, so that will take 100 nanosecond. Okay, and optimization is done on the cache to reduce the miss rate. Okay, so they have tried to increase the hit rate. Okay, so first of all, let us write this. Hit rate is 0.8 and access latency is how much? 10 nanoseconds. And penalty is how much? 100 nanoseconds, right? Now optimization is done to reduce the miss rate. However, the optimization results in an increase of cache access latency to 15 nanoseconds. Now they have tried to increase the hit ratio. Let me write it HR dash. But when they increase the hit ratio, the access latency increases to 15 nanoseconds. Okay. Whereas the miss penalty is not affected. So the miss penalty is still how much? 100 nanoseconds. The minimum hit rate rounded off to 2 decimal places needed after the optimization, such that it should not increase the average memory access time is. So they are asking that this was the hit ratio first, this was the access time, this was the penalty. Now they have tried to improve the hit ratio, but because of that the access time has increased and penalty has remained the same. So what must be the hit ratio minimum such that the overall average time to access does not increase? Means either it remains same as old one or it is better. Okay. So what I will do is I will calculate the average time for this. Let me say average 2, and I will calculate average time for this. Let me say average 1. And then finally I will say average 2 must be less than equal to average 1. Okay. Now average time of 2 will be how much? See, let us assume that the hit ratio is H, okay, where H will be between 0 and 1. If there is a hit, you take 15 nanoseconds to get the data, okay, plus if there is a miss, so how many chances are there? What is the probability of a miss? 1 minus H. So when there is a miss, it takes 100 nanoseconds. So this is the average time. This is the average time, no? See, let's say out of 100 fruits, you have 20 fruits whose cost is 50 rupees and you have 80 fruits whose cost is 30 rupees. So how do you calculate the average? 20 into 50 plus 30 into 80 divided by 100. So can I say 0.2 into 50 plus 0.8 into 30? So this is the percentage of these fruits from 0 to 1 probability, you can say, and the cost of that fruit, and this is from 0 to 1 and the cost of that fruit. That is what I have done here. heat ratio into 15 nanosecond plus 1 minus heat ratio into 100 nanosecond must be less than equal to, what is the heat ratio here? 0.8. What is the excess time? 10 nanoseconds plus what is the miss? 1.2, 1 minus 0.8, right? The miss is how much? 0.2 and the penalty is 100. Okay, if you solve this equation you will get the value of h. So it will be 15h plus 100 minus 100h. So it will be 100 minus 85h is less than equal to 8 plus 20, that is 28. So 85h must be greater than equal to 72. Heat ratio must be greater than equal to 72 divided by 85. Tell me what is the value for this? Please tell what is the hit rate and excess latency and miss penalty. See, this is your cache memory. This is your main memory. Okay, whatever data you need, that block is taken here into cache memory. Now, whenever you need some data, if it is already present in the cache memory, then it is called a hit. And the time taken to get that data is called excess latency. If the data which you want is not present, you need to bring it from main memory to cache memory. This is the penalty time. And when you don't get the data present in the cache memory, then that is called a miss. Okay. What is the value for this? Calculate. 0.85. So your hit ratio must be at least 0.85. Okay, clear है? Everyone please reply quickly. Is this clear? Okay, great. Let's move on to next question. Okay, this was also asked in 2022. Try this question. So we are given the consider three floating point numbers A, B and C stored in register RA, RB and RC respectively as per IEEE 754 single precision floating point format. The 32-bit content stored in the register in hexadecimal form are given as below. Which of the following is true? So for this you should know how floating point numbers are stored as per IEEE 754 single precision floating point format. Once you know that, what you can do is you can decode these hexadecimal values into decimal values. Once you get the decimal values, you can tell which of the following is true and which of the following is false. Yes. So you should know how numbers are stored in single precision format. Okay. So let us understand that quickly a little bit. Okay. So single precision numbers of floating point are stored in 32-bit format. Okay. So let's say this is a 32-bit format, out of which there is 1 bit here which is the sign bit, there are 8 bits here which is the exponent bit, and there are 23 remaining bits here which is the mantissa. Okay, your number is so your floating point number is something like this, -1 key power sign into 1 point mantissa into 2 key power exponent. Okay, so your mantissa will be so this part after 1 point that is given here, so it is 1 point mantissa, this is -1 key power s. So if your sign bit is 1, -1 key power 1 will be 1, so your number would be negative. If your sign bit is 0, -1 key power 0 would be 1 and your number will be positive. And this is 2 key power exponent, so this is the exponent part. Okay, now here you get the bias exponent. Okay, you do not get the actual exponent. and bias exponent is true exponent plus 127 in case of single precision format. Okay, now I know for those people who do not know this, you have to mug up, but there are time limit today because we are doing previous year questions. Otherwise there is reason behind each and every of this. Okay, so you do not directly come to this. Okay, if I go step by step, then you will never forget this representation of how it came. Okay, and you will also not forget the biasing value. This is called biasing value. Okay, so the biasing in the true exponent is done with 127. Why it is done with 127 only, etc. But because we have some time constraints today, so I will be solving questions. So this is the format which you need to know. Okay. Yeah, I think in 2023 also something like this was asked. 0.847, actually rounding off to becomes 0.85. Okay. Okay, so this is the format. Now what we will do is we will decode these values into decimal. So this is what C14 and 6 zeros. Okay, so your A number is, see, initially they have written like this 0x. This is nothing but they are trying to say that it is represented in hexadecimal format. Okay, this is 0 and x. C14 and 6 zeros, it is C14. Okay, so first of all, this is in hexadecimal. How do you convert from hexadecimal to binary? Each number is represented using 4 bits. So your number would be, C is how much? 12, A is 10, B is 11, C is 12. 12 is how much? 8 plus 4. So C would be this. 1 is what? 4 is what? And remaining all are zeros. Now first bit is the sign bit, so this is the sign bit. Sign bit is 1, means number is negative. Next 8 bits are exponent bits, so 1 2 3 4 5 6 7 and 8, these are the exponent bits, and this is the mantissa bits. Okay, so your number is minus 1 की power 1 into, what is mantissa? 1 followed by all zeros, and mantissa is actually 1 point. So this after decimal value I have given there, so I can say 1.1 followed by all zeros. This is the mantissa. Exponent is how much? This 1 0 0 0 0 0 1 1 0 0 0 0 0 1 0. Okay, into 2 की power exponent. Now what is the exponent value? 1 5 zeros 1 0. So this is 2 and 128. So the exponent value is how much? 130. But this is the bias exponent. What will be true exponent? True exponent will be bias exponent minus biasing value, that would be 3. So into 2 की power 3. Okay, so can I say this is minus 1 into 1.1 into 2 की power 3? So can I say it is minus 1 into 1100? Now what is 1100? 8 plus 4 12. So your A number is minus 12. Okay, now I wanted to show you how it came, so I did it slowly. Now for B and C, let's do it quickly. If you have any doubt, you can ask me. B is what? 4 2 1 and remaining all zeros. B is 4 2 1 and remaining all zeros. 4 is how much? 2 is, 1 is, and all zeros. So this is the sign bit, this is the exponent, and this is the mantissa. So your number is positive. It will be what is the exponent value? Bias exponent is how much? 1 2 4 4 and 128, that is 132. True exponent will be 132 minus 127, 5, right? So what will be your B value? It will be, sign is 0, so the number is positive. This is the mantissa. Mantissa is 1.001, and after 1 there are all zeros, no need to mention them, into 2 की power 5. So this is 100100. What is this number? 1 2 4 8 16 32. 32 and 4 is 36. So your B is 36. How? Minus 12. See, this is the binary representation. Okay, and it is represented in 32-bit format. The first bit represents the sign, it is 1, so your number is negative. The next 8 bits represent exponent, but this exponent is bias exponent, so you convert it into true exponent. What is true exponent? It is bias exponent minus 127. So this value is 130, the 8 bits. You subtract 127 from that, you get 3, and this is the mantissa, 1 followed by all zeros. So when you put a mantissa exponent and sign value in this format, your number would be minus 1 ki power 1 into 1.1 into 2 ki power 3, that is nothing but minus 1 into 1.1 into 2 ki power 3, that is minus 1 into, now here see, if your number is 32.5 into 10 ki power 2, so when there is 10 ki power 2, you can shift decimal point 2 places to the right, so it is 3250, right? This is for decimal where the base value is 10. Similarly for binary, when the base value is 2, if it is 2 ki power 3, you can shift this decimal 3 position to the right. So this becomes minus 1 into 1100. 1100 is how much? 8 and 4, 12. So your number is minus 12. Okay. 1.1 is binary or decimal. This is all binary. Finally, I wrote the decimal value minus 12. Okay. Similarly, this is 36. Now let's take the value of C. C is what? 414 followed by zeros. 414. 4 is what? 0100. 1 is 4 is followed by all zeros. Sign bit is 0. What is the exponent? Exponent is this, and this is the mantissa. Okay. So your number is positive since the sign bit is 0. What is the bias exponent value? 2 and 128, that is 130. What is true exponent? 130 minus 127, that is 3. So your number is 1.1 into 1.1 into 2 ki power 3, which is nothing but 1100, which is nothing but 12. Okay. So your A is minus 12, B is 36, and C is 12. Okay. A is minus 12, B is 36, and C is 12. Now check the options. A plus C is 0. Yes, it is true. Okay. Which of the following is false is dashed. Okay. So this is true. A and C are minus of each other. C equals to A plus B. C equals to A plus B. A plus B is 24. 24 is not equal to 12. So this is false. B equal to 3C. B equal to 3C. Yes, 12 into 3 is 36. This is true. B minus C is greater than 0. B minus C is 24. It is greater than 0. This is also true. It is asked which one of the following is false. So your answer is B. Okay. Is this clear? Guys, please keep replying quickly, okay, so that we can cover more things. If you have doubt, then ask. If you do not have doubt, just reply quickly that it is clear. Okay, great. Let's move on to the next question. Okay, very good question. Please pay attention here. Okay. Thank you so much, sir. Welcome, Pranav. Okay. Let's solve this question. Okay. And don't get frightened. Okay. See, I'll solve this question. You'll know. What it is saying, consider a system with 2 kilobyte direct mapped data cache with a block size of 64 bytes. Okay. So let's first start noting down the things. So your cache memory is 2 kilobytes, block size is 64 bytes. Okay. The system has a physical address space of 64 kilobytes and a word length of 16 bits. Okay. So your word is of 16 bits, so I can say 2 bytes, and physical address, that is the main memory, it is of 64 kilobytes. Okay. During the execution of a program, 4 data words PQRS, this was also asked in 22. During the execution of a program, 4 data words PQRS are accessed in that order 10 times. Okay. So during the execution, there are 4 data words PQRS. They are accessed like this. First you access P, then you access Q, then you access R, then you access S. Now again you access P, then Q, then R, then S. Then again you access P, then Q, then R, then S. ऐसा करते 10 times. Okay. Okay. Hence there are 40 accesses to the data cache altogether. Okay, so in the cache memory it will check for these data items. Okay, and total there are 4 items accessed 10 times, so total 40 accesses will be there. Assume that the data cache is initially empty and no other data words are accessed by the program. So initially the cache is empty. Okay, the addresses of the first bytes of PQRS are this. Okay, the starting address of all these bytes are given. For the execution of the above program, which of the following statement is or are true with respect to the data cache? And there are 4 options given. Okay, whenever every access to S is a hit, once P is brought to cache, it is never evicted. At the end of the execution, only R and S resides in the cache. Every access to R evicts Q from the cache. Okay, so let's solve this. So we basically want how PQRS are accessed. We can answer the questions. What are the addresses of PQRS? That is A248. Let me write it here. P is A248. Q is what? C28A. R is what? CA8A. Address लिखने में कुछ गलती हो जाए तो बता देना. And S is A262. Okay. Okay. Now first of all we need to so what will be our approach? We will see how the cache memory, how the blocks are presented in cache memory. What it is direct mapped. Okay, it is the direct mapped. Okay, so what will happen is let's say this is your memory and this is your cache. So each and every block in cache can have let's say this is cache, so the images of cache will be present in main memory. Okay, so let's say this is your main memory. So let's say this size is P, so it will be divided into blocks into sets of P size. Okay, now block 0 of every set can go in block 0 of cache only, it cannot go anywhere else. Then block 1 can go in block 1 only, block 2 can go in block 2 only. Okay, and so on. So if this size is P, the main memory is divided into blocks of P sizes, and let's say there are 256 blocks in one this part. Okay, one image. So one block can go whatever the number of block may be, it would be from 0 to 255. So let's say the block number is 12 of this image. So it can go in block 12 only, that is direct mapped. Here there is block 12, it can go in block 12 only. So if the block 12 of here is present, then this will replace it. Okay, that is how it will work. So we need to first of all find what is the cache memory size. It is 2 kilobytes. So you see here here what will happen is, this is direct map. First of all the block size is how much? 64 bytes, and cache memory size is 2 kilobytes. So number of blocks would be how much? 2 kilobytes by 64, 2 into kilo is 10, block size is 2 ki power 6. So this is how much? 2 ki power 5. There would be 2 ki power 5 blocks. Okay, now here if we see, then what we will get? Block 0 can come in block 0 only. Here also it can come here only. So we will need to decode this address, right? But before that we need to work out on some more things, right? This is your physical memory of 64 kilobytes. Okay, this is your cache memory. Cache memory is how much? 2 kilobytes. So this would be divided into images of cache. So how many images would be there? 32, because this is 64 kilobyte, this would be 2 kilobyte. Okay, so it would be divided into 32 such images. Okay, 32 parts, right? So if I look at the address, what would be the address of any block here? It would be something like this. Tag number means which part it is, right? Then inside you have the tag number. Inside the tag you have inside tag you will have block number, right? So you will have block number and then you will have the offset, right? So tag number is, it is 32 parts, right? So you need 5 bits to represent the tag number, right? So this will take 5 bits, right? Now inside it, how many blocks are there? In one tag, in one image you have this many blocks, so it will take also 5 bits, right? And total length is how much? Physical address is 64 kilobytes, so it will be 2 ki power 6 into 2 ki power 10, right? This many bytes, so it is 2 ki power 16 bytes. So you need 16 bits to store the 16 bits to represent the physical address. So the remaining is 6. Total is 16, na? First of all, clear till here? Just tell me. I'll do one message by that time. Everything clear till here? Okay, great. Now what we need to do? We just need to decode this into this format, which tag it's belong, which block it's belong, and what is the offset, right? And if two are from the same block, then they will come in the same block here also. For example, it is how many blocks? 32 blocks, right? So it would be 0 to 31. So the 15th block can come in 15th block number only, and the 15th block of this image, if it wants to come, it need to replace the 15th block of this, because it is direct mapped cache. So 15th block of every image can come in the 15th block only. Okay, so if there are two data items which have the same block number, then they will replace each other and so on. These are the options. So let us see. So now let's decode it. Okay, so what I will do is, okay, and let me take this also. Okay, now let's decode the addresses. One is P is 8248. Also one more thing I would like to tell you people, if you have such kind of things, write the addresses one below another. Okay, write the addresses one below another, and the bit should also match, so it is easier for you to observe. Okay. So P is what? It is A248. A248. A is what? 10. 10 is what? 8 plus 2. 2 is what? 2 is 2. 4 is what? 4 is 4, and 8 is 8. So this is your address for P. Q is what? C28A. C is what? A is 10, B is 11, and C is 12. 12 is 8 plus 4. 2 is 2. 8 is 8. A is 10. 10 is 8 plus 2. R is what? CA8A. C is 1100. A is 10. 1010. 8 is 1000. And A is 1010. What is S? It is A262. A is what? 10. 2 is this. 6 is this. And 2 is this. Okay, so you have written the addresses of all the data items. Now what it is asking, every access to S is a hit. Now see what will happen. when you can say every access to S is a hit, when you get S already present, okay, in the cache memory. Okay, so here you see the block number, so I can put a line here. This is the tag number, this is the block number, and this is the offset. Okay, so what I can see, the block number for P and S are what, same. Okay, so if P comes here and then let's say S is somewhere in other image, so if S comes here it will remove P, but if the tag of P and S are also same, then it will not remove it. So let me match tags of P and S. It is 10100, 10100. It means P and S are from the same image and from the same block. It's just that their offset is different. Means this is the block in which P and S are present. So P data item is somewhere here and S data item is somewhere here. Okay. Now how are we accessing the data? We are accessing PQRS, 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 and so on 10 times. Okay. So let's say you access P. So P will come somewhere in the cache memory, right? Now the block containing P will come somewhere in the cache memory. Now S is contained within the same block, so you do not again need to bring that block. So S will always be hit because when you access P, S is already present there, okay, in that block only. But here you should also check that Q and R are not replacing P, because if Q and R are replacing P, then when S comes, it again needs to get the value. So let's check for Q and R. Check the block number. Does the block number of P and Q is same? No. Does the block number of P and R is same? No. So if P is here, the block containing P data item is here, the block containing Q and R data item will be somewhere else. Okay, so what will happen is, first of all, when we'll access P, cache is empty, so from here the data block which contains P will come into the cache memory. Now Q and R will also come, but it will not affect P because the block number are different. When you try to access S, it is in this block only, so it will not go to main memory, it is a hit. Then again when you access P, P is also already present, Q and R will not affect P, and S is also already present. So every access to S will be a hit. This option is correct. Once P is brought to the cache, it is never evicted. Is that true? Let's see. The block of Q and R is also not matching. So once P is brought, it will never be removed. That is true, right? Because that block is not required by Q and R, and S is the same block. Okay. Then at the end of the execution, only R and S reside in the cache memory. That we will have to see. Every access to R evicts Q from the cache. Okay. Let's see. So now let's see Q and R. Now if you see, Q and R have the same block number. So let's say Q, the data, but they have different tag number. This is the tag number of Q and this is the tag number of R. So Q is present somewhere here and R is present somewhere here in some other image, but the block number is same. So what will happen? Let's say first of all P will be accessed, then Q will be accessed. So this block containing Q will come here. Now R will be accessed. Now R is here and R and Q have the same block number. So R also wants to go here only because it is direct mapped. So this block containing Q will be removed and R will come. Okay. So first here it was the block containing Q. Now it will be removed and R will come. Then S will be accessed, S will be here only in P. Then again Q will come. Now when Q will come, this block will come here. So this R will be removed and Q will come. Then again R will come here, Q will be removed and R will come, and this process will keep happening. So at the end what will happen? You will have the, see, for the last time what will happen? This is the 10th time. PQRS. So P is already there. Q will come from here to here. Then R will remove the block containing Q, and S is also present here only. Okay. So at the end of 10 operations you will have P, S and R in your cache memory. Okay. Now read, at the end of the execution only R and S reside in the cache. No, P is also there, and every access to R evicts Q from the cache. That is true. Whenever R wants to come, it and R and Q are in the same block number, so it will remove Q from the cache memory. So your answer would be A, B and D. Is this clear? Let me know. I am not clear what offset is. Do you mind explaining? No, not at all. And tag, you have written one more thing above, so is that clear? Tag is the number of image in the memory. We did 32 division for an image. Now tag represent that number, whereas block is the division we made in those images according to cache divisions. Yes, you are not clear with the offset. What is the block size here? 64 bytes. What is the word size? 2 bytes. So one block is of 64 bytes. Each word is of 2 bytes. So how many words would be there inside one block? 32, right? So you can also access them, right? But why there are 32 addresses, but total size is 64 bytes. So that's why you require 6 bytes. So in one block, where are you present? Where is your data present? This is the block. Is your data present here? Is your data present here? And so on. That's why that is the offset. Is it clear now? Is it clear, Pranav? Shall we move to next question? Okay, great. Let's move to next question. Okay, this was also asked in 2022. Try everyone. Okay, let's solve this question. What does it say? A processor X1 operating at 2 GHz has a standard 5-stage RISC instruction pipeline having a base CPI cycle per instruction of 1 without any pipeline hazards. Okay, so we have a processor whose frequency is 2 GHz and it is a 5-stage pipeline. So stage is 5, base CPI value is 1. For a given program P, that is 30% of branch instruction, control hazards incur 2 cycle stalls for every branch. Okay, So a program P has 30% branch instructions, and for each branch instruction it gets 2 stalls. Stalls means bubbles, okay, the time which you cannot use. A new version of the processor X2 operating at the same clock frequency has an additional branch predictor unit that completely eliminates stalls. So there is another version of the processor with the same frequency, okay. It has a branch prediction unit. So branch means what? Whenever there is a for loop or if else condition, whenever there is a function call, or when the for loop ends, or if else conditions, etc. So it has a branch prediction algorithm, branch prediction unit. So it predicts where the next instruction is going to be, which eliminates stalls for correctly predicted branches. So if it predicts the branches correctly, there will be no stalls. There is neither any savings nor any additional stalls for wrong predictions. What does that mean? If the prediction is right, there will be no stalls, but if the prediction is wrong, there will be no additional stalls and there will be no savings also. So the number of stalls will be 2 only if there is a miss. Okay, clear hai? For wrong predictions. There are no structural hazards and data hazards for X1 and X2. So we assume no structural and data hazards, only branch hazard. If the branch prediction unit has a prediction accuracy of 80%, okay, so branch prediction accuracy is 80%. The speed up hazard for X1, the speed up rounded off to 2 decimal places obtained by X2 over X1 in executing P is, okay. So what is the formula for speed up? Speed up is performance of new upon performance of old. Let's say the new one is 5 times faster, so it would be 5 upon 1 or 10 by 2, which is ultimately 5. I can say performance is inversely proportional to time. More the time something takes, less is the performance. So I can say execution time of new upon 1 upon execution time of old. This I can write it as execution time of old upon execution time of new. यहाँ तक क्लियर है, सब फॉलो कर पा रहे हैं, ठीक है. Now what is the execution time for old? See, 30% of the branches it requires 1 cycle per instruction, but in general, on an average, if 30% of the total instructions are branch instruction, and if each instruction gives 2 stalls more, then can I say that per instruction it will increase how many stalls? So number of stalls incremented per instruction would be, this is 30% is branch instruction, so 0.3 into 2, which is equal to 0.6. These many stalls will be more per instruction, okay. So you understand it like this. Suppose there are 100 instructions, okay, and clock cycle per instruction is 1. Now 70% are not branch and 30% are branch. So this will require 70 cycles only. This will require how much? There are no and data. This will require how much? It will in 2 cycle stalls. So 30 plus 60 I can say. 30 is the original and these are the stalls. Each will get 60 stalls. Each will get 2 stalls. So total 60 stalls will be there. So total number of instructions will be how much? 70 plus 30 plus 60, that is 160, out of which 60 are for stalls. So if I divide this 60 by 100, then per instruction I can say on an average 0.6 stalls will be incremented. That is what this value gives. Per instruction 0.6 stalls are extra, that is what I can say, because total is how much? 100 instructions, total cycles is 160. So 160 by 100 will be 1.6, out of which 1 cycle every instruction takes. So 0.6 is the stall per instruction because of this 30% branch instructions, okay. So what will be the time taken? It will be, time taken will be each cycle, so number of clock cycles divided by frequency, can I say? I can say the time, execution time is what? Number of clock cycles per instruction into number of instructions into cycle time. By total this many instructions are there, this is number of clocks required for one instruction, and this is one cycle time. Okay, now so for old it would be average CPI is what? 1.6. number of stalls per instruction is this. So originally one instruction required one cycle, now it will require 1 plus number of stalls per instruction. So this will be your new CPI, it will be 1.6. So this will be 1.6 into total number of instructions into cycle time. Cycle time is 1 upon frequency, that is 1 upon 2. Right? Now for new number of instructions will remain same only. This I have to calculate CPI and the frequency is 2. So this number of instructions get cancelled out, 2 also gets cancelled out because they are working at same frequency. So it would be 1.6 upon average cycle per instruction. Now what would be average cycle per instruction for new? It would be 1 plus number of stalls per instruction again. So I need to find out total how many stalls will be there. Now you see the program is same. So it has 30% branch instructions, but out of that 80% the branch prediction unit finds correctly. So out of 30% of the branch instruction, 80% of the time this branch prediction unit will tell me the address of the next instruction correctly. So out of this only 20% I will get miss. So the total number, number of stalls per instructions would be how much? It would be 0.3. These are the 30% branch instruction into 0.2. This much time my branch prediction unit will give me wrong answer into number of stalls, that is 2. This will be how much? 0.3 into 0.2, 0.06 into 2, that is 0.12. So here it would be 1 plus 0.12. So it will be 1.12. So this would be 1.6 divided by 1.12. Calculate and tell me what is the answer for this. .43. Okay, so 1.43 would be your answer. Is this clear everyone? Any doubt? Then let me know. Otherwise we'll move forward. Any doubts? Hurry up guys please, so that we can move on to next questions. Reply quickly guys. Is this clear? Okay, great. Let's move on to next question. Okay, so that's all from 2020. Now we are in 2022 is over. These are 2020 questions. Okay, what does this say? A direct mapped cache memory of 1 MB has a block size of 256 bytes. The cache has an access time of 3 nanosecond and a hit rate of 94%. During a cache miss, it takes 20 nanoseconds to bring the first word of a block from the main memory, while each subsequent word takes 5 nanoseconds. The word size is 64 bits. The average memory access time in nanosecond is. So see, first of all, the image should be clear in your mind what's happening. Okay, if it is clear, then you will be able to solve these questions very easily. This is your cache memory. This is your main memory. Okay, now a direct mapped cache memory of 1 MB has a block size of 256 bytes. The cache has an access time of 3 nanoseconds. What does that mean? When you want to get a data and if it is already present in a cache, it will take 3 nanoseconds for you to get that. Okay, so the access time when you have a hit is 3 nanosecond and a hit rate of 94%. So 94% of the time whenever you want the data, it is present in cache memory. During a cache miss, it takes 20 nanoseconds to bring the first word of a block from the main memory, while each subsequent word takes 5 nanoseconds. What does that mean? Suppose the data which you want is not present in cache memory, so you will have to bring it from main memory. Now from main memory what will come? A complete block will come, because the main memory is divided into blocks, cache memory is divided into blocks, and one full block is brought here, right? So a block will come into cache memory whenever there is a miss. Now how does the block come? It takes 20 nanoseconds to bring the first word of a block from the main memory, while each subsequent word takes 5 nanoseconds. Word is the smallest addressable unit. Now to solve this question, you do not need this knowledge, but I am just telling. Why does so? Your block, this is the block which you will bring from main memory to cache memory. It has words in it. Now why does it take 20 nanoseconds for the first word and only 5 nanoseconds for the remaining words? Because if you want this full block, first of all you need to do some address calculation and all and go to this block. So it will take 20 nanoseconds to get this word. Now what you need? Now you just need to go to consequent addresses. Okay, now there is no address calculation or anything, so the time reduces to 5 nanoseconds. Okay, so if you want to, this is your main memory, this is your cache memory. If you want to bring a block from here to here, this block, if I magnify it, it will be divided into words. So how it will come? First word will come, then second word, then third word, then fourth word, then fifth word, and so on. Okay, so whenever there is a miss, how much time it will take? It will take 20 into 1, that is the first word, plus remaining number of words into 5. This much time will be taken to get one block into the cache memory. Okay, now so we need to count how many words are there per block. So number of words in a block are how much? Block size divided by word size. Block size is how much? 256 bytes, and word size is how much? 64 bits. 8 bits is 8 bytes. So this is how much? 2 ki power 8, and this is 2 ki power 3, this is 2 ki power 5. So there are 32 words, right? So whenever there is a hit, you get 3 nanoseconds. Whenever there is a miss, you need to bring that block into the cache memory. In that block there are total 32 words, out of which one word will take 20 nanoseconds, the first word, and the remaining 31 will take 5 nanoseconds. So it will be 20 plus 155, that is 175 nanoseconds, right? The average time of access is how much? So average time is how much? Let us assume that hit and miss are of your hit ratio is given how much? 0.94%. So the average time would be how much? 94% of the time you will get a hit, it will take 3 nanoseconds, and remaining 0.06% time you will get a miss, it will take 175 seconds. Calculate and tell me what is the answer. What's the answer, guys? Hurry up, calculate and tell me. What will be the answer for this? Point 94 into 3, that is 2.82, plus how much will be there? 0.06 into 175, right? So it will give you 13.32. Okay, is this clear? Okay, let's move to next question. Again the same question. Consider three registers R1, R2 and R3 that stores numbers in IEEE 754 single precision floating point format. Assume that R1 and R2 contain the values in hexadecimal notation this and this. If R3 is equal to R1 and R1 by R2, what is the value of R3? Okay, how will you get this? You convert this and this into decimal, find R3, then convert it back to floating point format and then back to the hexadecimal format. Okay, we shall start. Okay, so your floating point single precision format is what? 1 is the sign bit, 8 are the exponent bit and remaining 23 are mantissa bits. Okay, and your number will be minus 1 key power sign bit into 1 point mantissa into 2 key power exponent. Okay, and here what you get is biased exponent, which is equal to true exponent plus 127. Here this exponent is true exponent. Okay, so you need to take the true exponent value and put it there. So let's find out the values for R1 and R2. So R1 is what? 422000000. 4 is how much? Let's convert it into binary so that we get 32-bit format. Then we will find sign, mantissa and exponent and put it in this format and get the decimal value. 4 is 0100, 2 is 0010 and remaining all are 0. This is the sign bit, sign is positive. This is the exponent. Now this exponent is biased exponent. Biased exponent is how much? 4 and 128. So it is 132. So your true exponent will be how much? 132 minus 127, that is 5. And this is your mantissa. So your number R1 would be, a number is positive, sign bit is 0, it would be 1.01 into 2 key power 5, which will be 101000. This is how much? 1, 2, 4, 8, 16, 32. So 32 and 8. So your R1 is how much? 40. Clear hai? Now let's find R2. R2 is how much? C12. Again convert it into binary. C is how much? 12. 12 is 8 and 4. 1 is this, 2 is this and remaining all are 0. This is your sign bit, this is your exponent, and this is your mantissa. Sign is minus, so your number is negative. Okay, so this will be how much? Biased exponent is how much? 2 and 128, that is 130. So your true exponent would be 127 130 minus 127, that is 3. So your R2 is minus 1 into, this is your mantissa 0 1 into 2 की power 3, which is equal to minus 1010, which is nothing but minus 10. So your R1 by R2 will be equal to 40 by minus 10, which is minus 4. Now minus 4 you again want to convert it into hexadecimal and into floating point format and represent it in hexadecimal format. Okay, so minus 4 I can represent, first of all minus 4 I need to represent in this way. Okay, so minus 4 can be represented as minus 1 की power 1 into mantissa is what? 1.0 into 2 की power 2, because 4 is what? It is 100, right? I can put a decimal here and write it as 2 की power 2. So this is like this. So your sign bit is 1, exponent, true exponent is 2, and your mantissa is 0. All zeros, okay, after decimal. So your bias exponent will be 129. Okay, just a second, here did I did any mistake? This was true biased exponent was 128 plus this. Okay, so your this will be your biased exponent. So what will be your number? Sign bit is 1, biased exponent is 129. It would be this 128 plus 1, and mantissa is all zeros. Now I want to represent in hexadecimal format. So take 4 numbers at a time. This is how much? 1100, that is 12. 12 is C. Take another 4 digits. This is 0. Take another 4 digits. 1 followed by 3 zeros. That is 8, and all remaining would be 0. So your answer is C08 and all zeros. Your answer is C08 and all zeros. B is your correct answer. Is this clear? Guys, please reply. Is this clear? This floating point format is asked multiple times, okay, in recent time. Cache, memory, floating point numbers, pipelining, these are the favorite topics to ask in COA. Was the previous question clear, guys? Okay, let's do this last question for today. What does it say? Consider a non-pipeline processor operating at 2.5 gigahertz. Okay, so there are a lot of information, so let us write here. Non-pipeline processor operating at 2.5 gigahertz. It takes 5 clock cycles to complete an instruction. So clock cycles per instruction is 5. Overheads associated with pipelining force you to operate the pipeline processor at 2 gigahertz. So let's say you converted this non-pipelined into pipelined. So because of overhead, the processor gets reduced to 2 gigahertz. Okay, so this is the pipelined processor. It operates at 2 gigahertz. Okay. In a given program, assume that 30% are memory instructions, 60% are ALU instruction, and the rest are branch instruction. Okay. In a program, 30% are memory instruction, 60% are ALU instructions, and the remaining are branch instructions. Okay. 5% of the memory instruction cause stalls of 50 clock cycles each due to cache misses. What does it say? Out of this 30% memory instructions, only 5% of the memory instructions cause stalls. And how many stalls are there? 50 stalls each, okay, for each instruction. Okay, 50 clock cycles each due to cache misses. So 50 clock cycles. And 50% of the branch instruction cause stalls of 2 cycles each. So 50% of the branch instructions cause 2 clock cycles stalls each. Okay. Assume that there are no stalls associated with the execution of ALU instructions. Here there are no stalls. Okay. For this program, the speed up achieved by the pipeline processor over the non-pipeline processor rounded off to 2 decimal places is. So we want to find speed up, that is performance of pipeline processor upon performance of non-pipeline processor, which is performance is inversely proportional to time. So execution time for pipeline processor into 1 upon execution time for non-pipeline processor, which is execution time for non-pipeline processor upon execution time for pipeline processor. यहाँ तक फॉलो कर रहे हैं? ठीक है. Now I want to find execution time for non-pipeline processor. Okay, so if let's say there is only one instruction, so it will take 5 cycles, or let's say there are I number of instructions, but so I number of instructions, each takes 5 clock cycles and the frequency is 2.5 gigahertz. So I will write 2.5. Now here also total number of instructions is I for pipeline processors. CPI I need to calculate and the frequency is 2 gigahertz. Okay, I and I gets cancelled out, 2.5 and 5 gets cancelled out. I get 4 upon clock cycles per instruction of pipeline processors. What is clock cycles per instruction of pipeline processors? 1 plus number of stalls per instruction. I told you how it comes with real example in the previous case. So 1 plus number of stalls per instruction, it would be how much? Number of instructions in which there is a stall multiplied by how much stall it causes. So here out of, let's say if there is 30 out of total processes, there are 30% what? Memory processes, memory instructions. Out of that only 5% causes stalls and it causes 50 stalls each. Plus there are 10% branch instructions, out of that 50% cause stalls and 2 stalls each. So this will be how much? This will be 0.3 into 0.5 into 5 plus this would be how much? 0.2 into 0.5, right? This would be how much? 0.15 into 5 plus this is 0.10. 0.15 into 5 is how much? 0.75 plus 0.1, this is 0.85. So number of extra stalls per instruction would be 0.85, which is equal to 1.85. So your speed up would be 4 upon 1.85. What is the value for this? I think it is 2.16. Yes, the speed up would be 2.16. So that would be your answer for this question. Okay, any doubts? Okay guys, thank you for watching, thank you for joining. That's all for today. This was computer organization and architecture revision. Tomorrow we will be doing data structures and algorithms revision. We will be solving some of the previous year questions of data structures algorithms. Again exactly tomorrow we will be doing it at 11 AM. Okay, hope to see you there guys. Thank you.